So we're going to do some quick simulations in our in order to think about what simple regression is doing and sort of what our framework, what our foundation is that we're building on top of. So these are going to be extremely simple at first, but actually there's some lessons to be learned from these before we go further. So if you want to follow along, I posted, I'm updating a little bit. It should be some updated code with a few extra bits on Google Classroom. So load the libraries that we need. This theme set is not super important, other than I think a couple of the graphs, it makes them look like they are in the book. And you may need to do some tinkering to get rStanArm to load, or any of these others if they have certain dependencies, and depending on your version, all kinds of weird stuff. If you have trouble, write something in Piazza tagging RStudio or R as the topic, and we'll try to set you up either with the help of your TA or DAX staff who may have some additional experience working with some of these things. Or I'll try to help as I can, but often it's maybe particular to your setup on your computer if there's an issue. Okay, so what are we doing? We're going to start by making a regression model. So we're putting on our omniscient hat. So not the outlook of the researcher, but the sort of nature unfolding, kind of modeling the data generating process in a very simple model. Here, X is just the sequence of numbers 1 through 20, and our length of the data vector there is going to be 20, of course, because the length of X is 20. These are going to be true coefficients of a generating regression model, A and B. A is 0.2, B is 0.3. And we're going to need, we have those epsilons added on, and so this is going to be their standard deviation. So they're going to be randomly distributed, normal centered on 0, standard deviation of 0.5. We haven't done any of that yet. We're just setting the parameters. Again, in real life, we don't set the parameters, we estimate them. Set the seed to 2141 if you want the simulation to look exactly like mine. Mess around with other seeds to see how random noise, simulation noise, is going to vary it. Okay, and here is the generating process, right? We're going to create some Y observations that are coming out of this regression model, right? Intercept plus slope times X. Remember X, what is X? That those data are just really simple sequence. One data point has X equal to 1. And actually you can look, oh no, I forget, it's not a data frame. It's, all right, I can, if you want to see here, right? X is just the sequence from 1 to 20, really simple, not randomly generated settings for X, for the predictor, for the independent variable, if you will. And so we're taking intercept plus B times X plus we're randomly normal, random normal distribution. So for each of those 20 observations, we're going to take our 0.5 sigma times a standard normal. We could also just set epsilon equal to this thing and add epsilon in. That would look more like what you're used to seeing. And we're going to create a data frame by putting those two vectors, X and Y, together. And now I can actually look at, if you want to inspect in sort of spreadsheet form, click on fake, and you can see the pseudo data that we created, right? Data, the observation 1 has X equal to 1 and Y equal to 1.2 something, and so on. Okay. All right, so now we're going to fit We're going to use the standard function from this book for fitting regressions, which are done in a Bayesian style. We're not focused until a few chapters from now on sort of some differences between Bayesian estimation and frequentist estimation and how we can interpret those, but we've done a little bit of setup in earlier chapters. And we'll sort of start talking about these with the understanding that we're not going to go too deep into the differences in interpretation. But let's fit it both ways. We're going to fit, and it'll tend to take a little bit longer. It's very quick. This is very simple. Few data points. On some of the other data, it'll take longer than the frequentist estimation, just because it's using simulation to get estimates here, so it can take longer. And let's read through what the results are for a moment, right? So this is regressing y on x. There are two predictors because it's always including the intercept, right? And our best estimates that they're giving for A and for B. It doesn't say A and B, but it says the intercept and x, essentially the predictors. One is just a intercept, which is like multiplied times 1, a bunch of ones, and x is 1, 2, 3, 4, all the way to 20 in this case. Very simple data. So this is saying my best fit for A is 0.41, and my best estimate of B is 0.28. It's using a median of a posterior distribution for those. Again, that's something we'll get into in talking about Bayesian interpretations, but it's a sort of a typical draw from plausible values for A and B. And sort of reasonable version for, you could actually do this in frequentist approach as well. It's usually you see standard error, which is a standard deviation. This is a median absolute deviation. And in fact, if you think about how you would think about spread of something that you want to measure their variation, it's always a little bit convoluted to talk. Our instinct to say is how far typically away is an observation from its mean. This is giving how far typically an observation is from its median, and the way we're defining typically here is instead of standard deviation, which there's the convoluted part, you have to do squared differences, right, and sum them up and take their square root. It's not exactly even an average. Here we are just literally taking how far away each observation is from its median, and then taking the median of all of those absolute differences, and then scaling it up in a way. They talk about this in chapter 5 of the Gelman et al. Book, to put it more on the scale of what we're used to seeing, which are standard deviations. You don't need to do that, but it's just to kind of make it a little comparable to doing the standard approach. Okay, so what is this saying? It's saying my best guess for A is 0.41, give or take, right? Typically about 0.22. If you want to be, if you want to have an interval that's has a higher probability of capturing the median, then maybe you could, really kind of using a sort of frequentist approach. This is not taking full advantage of what we have, which is essentially a posterior distribution over plausible values. But for old time's sake, we can say plus or minus 2 times this. But we could literally calculate the probability if we want, the probability of this intercept being between any two values we pick. And similarly, the more important piece, right, the slope is estimated as 0.28, give or take around 0.02 to 0.04 if you want. Notice we were estimating something that we actually know the answer to, right, because the intercept is 0.2, and right, not a great estimate, 0.41, but we said give or take 0.22 or maybe even 0.44 or bigger if we wanted higher confidence. So yeah, even the give or take our standard, our median absolute deviation is going to give us an interval that includes the truth of 0.2. And our slope estimate plus or minus around 0.02, maybe 0.04, 0.05, It's important to think about this in fuzzy terms because that's where significance testing gets us in trouble. Is there's a lot of noise and a lot of measurement and sampling error, and if we think we're being really precise, we're fooling ourselves. And so, getting a sort of a sense of a kind of a fuzzy interval that represents our uncertainty is actually more accurate in representing our true uncertainty, just in terms of communication. Although it's can be disappointing. So, right, we used a true slope of 0.3, and our estimate from the data was 0.28 plus or minus, so maybe 0.26 to 0.30 as a more likely than not, maybe 0.24 to 0.32 as a stronger probability that we're getting the truth somewhere in there, right? And we'll leave this out for now, but well, at least the uncertainty about it. But I'll mention this. I mean, so our best guess essentially at the at how what sigma is, right? Remember what sigma is here? It's the standard deviation of the errors, and this is we generally are looking at this is much preciser measurement, right? Like if you look at, we got it right on. We said, hey, think with this 0.50. So we're estimating essentially how much residual randomness there is, right? That's being added on to the structural piece. Okay, let's actually just look at what may be more familiar, which is using LM as the standard workhorse linear model function in R, regressing y onto x using the data which we named fake. It's going to give us a lot more information, including fancy stars, which we love. Oops, sorry, that was from a package I don't have installed. So same thing, right? Here are estimates. We had 0.41 and 0.28 as our estimates for intercept and slope, respectively. Similar, 0.39, 0.28. We've got our standard error, so we can say I've got a confidence interval of any percent I want. If I want to do a 95% confidence interval, I'll multiply this times 1.96, either of these, and add them on, subtract them. They will also give you a sense of uncertainty, which, as we've talked about, typically gets misinterpreted what they mean. But have at it if that's what you'd like. What is seeing 3 stars here? Does that mean this is a really big slope, a very strong relationship? No. All it tells me is, I can have to define myself what it means to be a relationship to be strong, and there's no way to know because this was silly made up data, and so I don't have any sense of what would be large in magnitude, what would be substantively or contextually significant. All this says is that more stars means I'm especially confident that this slope is not exactly equal to 0, right? It could be very, very small, but I'm really, really confident that it's not exactly 0. Okay, so that the strength of, or how large the p-value is, which is what these are, right, is telling me that. I'm less confident that the intercept is not 0 in this case, and in most cases, the intercept being 0 is not particularly meaningful, whether it is or isn't 0, right? Notice also one good thing it tells you is that the x is explaining a lot of the variation in y, right? 92% of, so it's sort of absorbing a lot of the randomness in y. Once you look at the residual around the best fit line, it's far less. So actually, let's plot it as they did in the book. This one was done in the book, so and there it is. You can also click to zoom. That doesn't always work when I'm recording for you to be able to see it. So, but there it is. There's the data points, and you can see that 92%, R squared. Right, what that amounts to is if you looked at the variation in y without fitting a regression line. If you just looked at how on this y, let's actually use the little bit nicer graph the way that the book does it. Sometimes when you don't need all this when you're just kind of examining things. It's not like for presentation, but there I've got some better labeling. The line is y equals 0.41 plus 2x times x. I'm just using the best fit slope and intercepts. And notice that, the residual, what we estimated is around 0.5, the typical variation around the line in a vertical direction, is relatively small when compared with, if we just look at the y value for all of these data points and how spread out they'd be on the y-axis, right? There's a lot of variation in our y values, but when we estimate or predict y values given the information contained in x, if I just say, hey, I'm going to take a random observation, where do I think y is? Well, on average, probably be around 3 or 4, but sorry, I think a garbage truck is going by. But if I had to, guess sort of or observe one after another y being generated, they'd be bouncing around all kind of through this range. But when I know what x is and I say, oh, okay, well, for this particular observation, x is 5, how much do I think y will bounce around the best guess? Not very much, right? Once I know what x is, there's very little additional variation. That's really what's captured by the r squared. Relatively little variation in y given x as compared to y when we didn't condition on x. Okay, hopefully that is helpful. All right, so I want to do. I'm gonna stop there and do a second video, probably two more videos after this that are closely related.